AWS EMR architectural capabilities. In this section, let's look at some of the architectural capabilities of AWS EMR. Okay, so what are the objectives? We're going to look at the performance of EMR, then we'll look at scalability, availability, configuration, security, logging, monitoring, cost model, and interfaces associated with the Elastic MapReduce cluster. Performance. Performance of an EMR cluster can be improved by tuning the Hadoop configuration files. There are several tunable configuration parameters in Hadoop. In fact, there are hundreds of parameters, but the EMR defaults that you get are pretty good. If you are an app developer, clearly you know more about your data and you know what kind of configuration works the best for your Hadoop. So you can tune those configurations if you want when you create the cluster. There is the Hadoop configuration section where you can say, for my core site and for my MapReduce site, for my yarn site XML files, these are the configuration parameters I want. So they do give you the capability to tune your Hadoop system based upon the Hadoop configuration. You can also improve the performance by choosing the right instance types. Don't forget that AWS EMR gives you several different instance types families. You have the general family, the CPU family, the memory family, and the disk I/O family. The general families are pretty good, you can use them, but if you want CPU intensive tasks, then you may want to use the CPU families. If you have memory intensive tasks running in your EMR cluster, then you may want to choose instances that give you more memory, versus if you have a cluster that has a lot of storage but not much processing, then you can go for machines that have a larger disk volume. So choose the right instance type so that you can tune your cluster accordingly for performance. You may want to use general purpose instances for the master node. The master node has, of course, computational requirements for the file system, which is the name node, and also it is also running the resource manager, and it's also running several of the ecosystem applications like Hive, Pig, etc. So general purpose is pretty good for the master. If you have a cluster with fewer nodes, smaller file system, consider smaller instance types that are general purpose types. If you have a cluster with large number of nodes, larger file system, consider larger instance types, which are general purpose types, or whatever types you may want to choose depending upon the kind of applications you may be running in your cluster. And don't forget that EMR allows you to run multiple clusters. You can create one cluster with certain configuration, another cluster with another configuration. These are just mechanisms for you to tune your cluster. Many of the jobs can also run on nodes using general purpose instances. Not only can you run master node with general purpose instances, you can also run jobs with that. Although I do have to tell you that if you want to tune it specifically, you're welcome to do that for memory or CPU. So you may want to use smaller instance types for testing, development, and smaller jobs, so smaller clusters. And you may want to use larger instance types for production or larger jobs. So you can play around with different kinds of instance types. You can play around with different parameters for the Hadoop configuration in order to create a cluster with the appropriate performance. Sometimes you want high performance, sometimes you don't want high performance, you just want it to be a simple cluster and not pay much. Continuing on the performance concept, use memory optimized instances for memory intensive processing. For example, if you do analytics using Spark, Spark likes to load all the data into memory, so you may want to use memory optimized instances. Use compute optimized instances for CPU intensive jobs. If you have reasonable amount of data but you really have to do a lot of calculations, for example mathematical modeling, or you want to do image processing, then you may want to use CPU optimized instances because they have more CPUs than RAM. Jobs such as parsing, machine learning can take advantage of compute optimized instances. Also use storage optimized instances for heavy HDFS workloads. Sometimes you may have a lot of data and your computation may not be as much. There's a lot of skipping of the data that you may have to do. So in that case, you may want to use storage optimized instances. Another classic example of that is when you're running HBase on your cluster. HBase is a NoSQL database that runs on a Hadoop cluster. If you want to do that, you're welcome to use the storage optimized instances. In terms of scalability, don't forget that scalability comes in two forms: vertical scalability and horizontal scalability. In terms of master node, there can be only one master node in a cluster. So you can only scale the master node vertically. So what you do is you get bigger boxes for the master node as you need it. In terms of compute nodes, if you want to do a lot of computational processing, then you can always vertically scale that too by getting bigger boxes. In terms of disk scalability, you can do that by getting bigger boxes with bigger instance storage, right? This is what I mean by the family of instance classes. You may want to choose the appropriate type. So you can always scale vertically the various instances. But the real value behind Hadoop is horizontal scaling. You cannot really scale the master node horizontally, you can only scale it vertically. But the rest of the processing, which is where the real work gets done in Hadoop, you can scale by adding more instances. For example, you can add more core and task nodes to scale horizontally. If you want to scale based on HDFS and processing, in other words, you want storage and processing, then you end up adding more core nodes. If you want to scale only processing, if you only want to add more processing, but you don't really want more storage, then you can add more tasks nodes. So that's how you scale horizontally when it comes to computation and storage. Availability. If the master node crashes, then the entire cluster comes down because the master node is the brains behind the cluster. So if the master node ever goes down, then the cluster terminates with errors and all the slave nodes also will die. So you've lost the cluster. But if a slave node crashes, then another slave node will be brought up automatically because you said you want to have 4 core nodes and 2 task nodes. Well, if one of the core nodes fails, then you will notice that it automatically brings up another one so that it can replace it. It's done automatically for you. And that's how availability is handled in the Hadoop EMR cluster. When it comes to configuration, don't forget there is something called bootstrap actions that you can configure to initialize your node instances. So that's something that you can do to configure your instance to install specific kind of software, to set some kernel settings, whatever you want to do inside the machine, you can do that. Then there is also Hadoop configuration. Hadoop has several configurations. There is core configuration, HDFS configuration, yarn configuration, MapRed configuration. There is Hive configuration, pig configuration. They're all these different site files: core site.xml, HDFS site.xml, yarn site.xml, MapRed site.xml, Hive site.xml. Those configuration files can be updated, can be changed when you create the cluster. You can set those values as part of cluster creation. You can always log into the instance and configure whatever you want. One of the cool things about AWS EMR is that they allow you to log into your cluster machine and then you can tune whatever you want within the cluster. So you always have that capability in AWS EMR clusters. In terms of security, security is very important when it comes to Hadoop because many companies are putting their data into the cloud, especially if it's a public cloud, and they want to make sure that nobody can hack into the data. They want to make sure that it's secure. So one of the first things is that the cluster runs inside a VPC, which is good. And the communication between the nodes, between the master node and the core nodes and the task nodes is all done using SSL. Hadoop has a lot of communication that goes on between the master and the slave nodes, and even between the slave nodes. All that communication has been configured to be done over SSL, so nobody can listen in and see what's the data that is being sent back and forth. The data that is stored in S3 or DynamoDB can also be made secure, and they are governed by IAM security policies. We also saw how in EMRFS you can actually say you want to encrypt the S3 file system, so that's also a possibility. There are also security groups that can be configured for the instances and for the master, core, and task nodes. The Hadoop ports are also closed by default unless you explicitly open it. there's a lot of ports that are open in Hadoop that allow the different machines to communicate with each other, but they actually shut all these things down and only allow the machines that need to communicate from to talk to them using the VPC. And so they have really locked down the cluster unless you explicitly open it by going into the network configuration. As far as logging is concerned, of course, every machine does its logging. All these logs are then aggregated into the master node. The data is actually placed, the log files are actually placed in HDFS under /mnt/var/log folder. You can find the Hadoop logs under /mnt/var/log in HDFS. You can find the step logs under /mnt/var/log/Hadoop/steps, followed by the step ID. Every step is given a unique ID, and so the step ID is the subdirectory under which the logs for that step are placed. There's also bootstrap action logs that are placed under /mnt/var/log/bootstrap actions /1, 2, 3, 4, whatever the bootstrap action number may be. And then the instance state logs. Every instance has its state, and those log states are placed under mnt var log instance state. So the logging is done and it's aggregated inside the HDFS, and then eventually it's copied or archived into the S3 file system, because that's where you want it to be. After the Hadoop cluster shuts down, you still may want to access the log files, and so everything can be archived into S3. And when you went through the configuration, you saw that you could actually do that. You can actually say where you want the log files to be in S3. When it comes to monitoring, EMR actually integrates with CloudWatch. There are 3 groups of monitoring information that's available. You can get information about the status of the cluster. You can get information about the node status. You can also get information about the IO status. The status of the cluster or cluster status tells you how many apps are running, how many apps are submitted, how many of them failed, the number of containers that have been allocated inside the cluster, the number of map tasks you can run, the number of reduced tasks you can run, the number of slots. Everything around the cluster information itself comes in the cluster status. There's also node status, which tells you how many nodes are running, how many nodes are lost, how many nodes are pending, and so on and so forth. And then in the IO status group, you get information such as how many bytes have been read from and how many bytes have been written to S3, how many bytes have been read from and written to HDFS, replication information, and all kinds of disk IO information is available in IO status. In terms of cost model is a very important aspect of Hadoop. The cost model with EMR is really the cost of EC2 plus a small price for giving you a PaaS solution, because they're giving you PaaS software on top of Hadoop. They're actually giving you the Amazon EMR Hadoop implementation, and so there is an upcharge for that. So really, the hourly charge is really the EC2 instance type charge plus the EMR upcharge. As I mentioned, EC2 instance hours are charged for the master, core. Cost model is extremely important for Hadoop because you're processing a lot of data, you may need a lot of machines to process them, and so the price can go up. So it's important to understand how the cost model works. First of all, the charges are done hourly, and the hourly charges include the EC2 instance type plus the EMR upcharge. Now, if the EC2 instance type costs 32 cents per hour, they may charge you 35 cents, about 10% upcharge, because they're installing the Hadoop software on top of it. The EC2 instance hours are charged for the master, core, and task nodes. So they actually aggregate all of them. Every one of those nodes are charged. And the EMR charges vary with instance types. We all know that different instance types have different prices associated with them. The cost model is also associated with storage such as S3, DynamoDB, and RDS. Don't forget, you may have your data in S3, you're being charged for that. You may have your data in DynamoDB, you're being charged for that, and same thing for RDS. You may bring in data from S3 and process it and put back the results in S3. You're actually being charged for all the data that you're placing in S3. So don't forget, there is a charge associated with that. That's a separate charge. Reducing the cost is an important aspect of Hadoop because you may be processing a lot of data and you may be bringing a lot of machines, and because it's hourly charged, you have to understand some of the nuances of that. If your job runs for 10 minutes, you will still be charged for the cluster hour. So if you got 10 machines that you launched for the cluster, 1 master and 9 slave machines, and you just ran for 10 minutes, then you will still be charged for the entire hour for all the 10 machines. So you don't want to be running lots of short clusters. You want to run a cluster and run a whole bunch of steps within that so that you can take at least an hour in order for you to do the processing, or close to the hour in order to do the processing. If you take 1.1 hours, you'll be charged for 2 hours, right? Use appropriate machine types, extra large, 2 extra large, 4 extra large. Remember, your memory requirements are critical because memory requirements determine what kind of a machine you want. If you need 16 gigs of RAM, then that's what you should choose first. And then you want to choose the closest number of cores that's associated with that. So start with memory, and then the virtual cores will come accordingly. Use the EC2 pricing models effectively. Remember, in EC2, you have on-demand instance types, reserved instance types, and spot instance types. If you're going to be running the cluster for the next a year or 2 years or 3 years, then you may want to go with some kind of a contract and get the reserved instance types. But if you're going to be running the cluster ad hoc, then you're okay with just doing the on-demand, like the one that we've been doing in the class. When you do on-demand, there is no upfront cost, but it's a bit pricey and there is no contract. But if you're going to be doing reserved, that means you're telling AWS guys that you want to sign a 1 year or a 3 year contract with them, but at a lower price. There is also something called spot instances, which is where you bid for instances from unused capacity. There's a lot of people that have bought instances, they have reserved instances into the future, but then they're not really using it, in which case they actually put it into the marketplace. You can go ahead and bid for those instances. And you can actually mix and match all these different types. You can use for your core, you may want to use on-demand or reserved, and for your task nodes, you may want to just go ahead and use the spot instance types. So you can actually mix and match. You may want to think about your cost, especially if you're dealing with a lot of data and a lot of processing. Let's look at how to reduce cost using spot strategies. If your node cannot fail, which is typically for the master and the core nodes, then you can run the master and core nodes on-demand, and then you can use the spot market to bid for task nodes. Remember, task nodes are things that you bid for. So for example, you may say, I want to pay 10 cents for a specific type of node. And if there are people that have reserved instances that they want to put in the market, you can bid it and you can get that particular task node. Now, if somebody outbids you, you lose the task node. Because the task nodes are not running any HDFS, there is no data loss. So it's okay for you to lose a task node. You'll get another one, but it's okay to lose one because you're not really losing any data. You don't want to do that in your core nodes. So spot nodes or spot instances from the spot market can be used for task nodes. If your cluster can fail, then you can run the master on-demand, and you can run the core and the task nodes on the spot market. It's okay for the core to fail too, because if the core fails, a copy of the data is in another machine. Typically, HDFS has a replication of 3. Every block is replicated 3 times. So if a core node fails, it's okay. Another core node will come in and replication will take place. So if you're okay with your cluster failing and then recovering from time to time, then you can go ahead and take the second approach, which is run the master on-demand and run the core and the task nodes on the spot market. Right? So there are a lot of different ways by which you can configure your cluster in order for you to reduce your cost. In terms of interfaces, there are several ways by which you can interface with EMR. You, of course, can interface with the AWS console, which is the graphical user interface to launch your cluster. That's what we've been doing. You can also use the AWS CLI, which is a client application that can be installed that run from your local machine. You can do that. You can also use the AWS EMR CLI, which is a special client application, which is the Elastic MapReduce client that AWS guys wrote that you can install in your local machine and you can run it. But don't use it because this has become deprecated now. You can also use the SDK, which is the software development kit. That's available for you. It's available in multiple languages. That's one way to interface with AWS in order to create a cluster, in order to create a job, in order to check the status of the job. And there's also the web service API that is available. In summary, when it comes to performance, you can improve the performance of your cluster by choosing the right type of machine. Don't forget there are different kinds of machines, different profiles of machine in AWS. You can choose the right one to get the right performance for your cluster. In terms of scalability, don't forget there are two kinds of scalability. There is vertical scalability and there is horizontal scalability. Master can be scaled only vertically. Slaves can be slaved both vertically and horizontally. You can scale the master and slave nodes vertically by using bigger machines. If you want to scale the compute and storage horizontally, then you can add more core nodes. If you want to scale only compute-wise, you only want to add more computational capacity, and that's horizontally, then you can add more task nodes. When it comes to availability, don't forget if the master crashes, everything goes down because master is the brains and all the slaves are connecting to the master. If the master goes down, all the slaves will also go down and the cluster will shut down with an error message. If the slave crashes, if any one of the slave crashes, another slave will be brought back up soon by the cluster. It does it automatically. You don't really have to do anything because you already configured the cluster to say, I want to have 4 core nodes and maybe 3 task nodes, and I'll make sure that it maintains that. When it comes to configuration, you can use bootstrapping to configure the machines on setup. You can also configure Hadoop properties at launch. You can even get under the hood of the cluster by logging into the cluster machines. It's an Amazon Linux, so you can log in and you can do whatever you want to do. When it comes to logging, logs are aggregated into the master and you can synchronize those logs into S3. When it comes to monitoring, EMR is integrated with CloudWatch. You have 3 major pieces of information or groups of information available: cluster status information, node status information, and IO status information. When it comes to cost model, don't forget EMR bills on an hourly basis and it's based upon the EC2 type plus an extra price for Hadoop management. You can use reserved or spot strategies to bring down the cost of your cluster. When it comes to interfaces, there are several different interfaces available for you to interface with EMR. There's AWS Console, which we've been using. There's also the AWS CLI, which is the command line interface tool. And then there's also AWS EMR CLI, which is an old legacy tool that you should not be using anymore. And then there is the software development kit, the SDK kit, which is available in multiple languages. And there is also the web service API that's available.